first review what we learned about point estimate, interval estimate, level of confidence. Then we're going to jump into the definition of t-distribution. Remember, a point estimate is a single value estimate for population parameter. The most unbiased point estimate of the population mean, or mu, is the sample mean x bar. In the next definition, we have the interval estimate. An interval estimate is an interval or range of values used to estimate a population parameter like population mean. Remember that we try to find a range of values or interval of values that are very close to population parameter. That's why we use the confidence interval. What was the definition of level of confidence? The level of confidence, C, is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. What was the definition of critical value? The critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. Remember that if you're dealing with normal distribution, for different level of confidence, we have different critical values. For example, if the level of confidence is 90%, the ZC or critical value is 1.645. If the level of confidence is 95%, you have 1.96. And when the level of confidence is 99%, you have 2.575. Guidelines to create or construct confidence interval for population mean in two different scenarios. If sigma is given to you, sigma or population standard deviation is given, we are following a normal distribution. The critical value is ZC. The very first step, verify that sigma is given, the sample is random, and it's a normal distribution, or the size of the sample is more than or equals to 30. In the next step, we find the sample statistics N and X bar. Why? Because we need to find the point estimate. Then we find the critical value, Z sub C, that corresponds to the given level of confidence. Then we move on to find the margin of error E, which is ZC times sigma divided by square root of N. In the last step, we find the left and right endpoints and form the confidence interval. The left endpoints is X bar minus the distance, X bar minus E, and the right endpoint is X bar plus E. The interval is going to be X bar minus E and X bar plus E. And you're going to say that, hey, we are 90% confident, we are 95% confident, or we are 99% confident, depends on what is C, that mu or population mean is bounded between these two numbers. In majority of cases, sigma or population standard deviation is missing. It's not given. There's either no study before, or the population was big enough that there was basically no practical work done to find the sigma or population standard deviation. In this case, instead of working with ZC, we jump into TC, which is for t-distribution. The steps are, first of all, verify that sigma is not given to you, or it's not known. There is no way you can find sigma. The sample is random, and either the population is normal or N is more than equals to 30. N is the sample size. In the next step, you find the sample statistics, N, X bar, and S. Remember, S is the sample standard deviation. The formulas that we introduced in descriptive statistics are given here, but eventually we use our calculators. In the next step, you identify the degrees of freedom, the level of confidence, C, and the critical value, T sub C. Why? Because these values help us to find the margin of error or distance, E. E in this case is T sub C times S divided by square root of N. Compare the distance or margin of error between these two scenarios. In the first scenario, sigma was given to you, so you could use sigma. But here, since sigma or population standard deviation is missing, you're using S, which is sample standard deviation. Now, in the last steps are the same. Find left and right endpoints. The left endpoints is x bar minus e, and the right endpoints is x bar plus e. The interval of confidence is x bar minus e and x bar plus e. So what is a t-distribution? If the distribution of a random variable x is approximately normal, it's not exactly normal, it's approximately normal, then t, which is equal to x bar minus mu divided by s over square root of n, follows a t-distribution. The critical values of t are denoted by t sub c. Here are several properties of t-distribution. This is the graph of t-distribution, which is similar to normal distribution, but it's not exactly normal. As you can see, the tails are shifted a little bit above. First of all, the mean, median, and mode of t-distribution are all equal to 0. 2, t-distribution is bell-shaped and symmetric about the mean. Number 3, the total area under the t-distribution is equal to 1 or 100%. 4, the tails in the t-distribution are thicker than those in standard normal distribution. 5, the standard deviation of the t-distribution changes with the sample size, but it is greater than 1. Remember that when we had a standard normal distribution, the standard deviation was 1. But here for a t-distribution, the standard deviation is greater than 1. Number 6, the t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. The degrees of freedom, sometimes abbreviated as df, are number of free choices left after a sample statistic such as x bar is calculated. Well, when you use a t-distribution to estimate a population mean, the degrees of freedom are equal to 1 less than the sample size, or the degrees of freedom df is n minus 1. And finally, the last property, as the degrees of freedom increases, the t-distribution is getting closer and closer to standard normal distribution. After 30 degrees of freedom, the t-distribution is very close to a standard normal distribution. So these are the properties of t-distribution. When you're working with confidence interval approximating population mean, you need to check to see if sigma is given or not. If sigma is given to you, then you're going to use ZC and sigma to find E, or margin of error. If it's not given to you, you're going to use T sub C and S, which is the sample standard deviation and the degrees of freedom, n minus 1. In using your calculator, when you want to create or construct a confidence interval, you're going to go to stat, then you're going to go to tests. So the very first thing you're going to select is stat, then tests. If the standard deviation of population is given to you, you're going to go to tests and select Z interval. However, if sigma is not given to you, in your calculator, you're going to select T interval. So that's the difference between these two. If sigma is given, yes, then you're going to use tests, Z interval. If it's not given to you, you're going to use T interval. Let's take a look at one example here. Question says, you randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit, and the sample standard deviation is 10 degrees. question asks us to construct a 95% confidence interval to capture the population mean of temperature of coffee sold and assume that the temperatures are approximately normally distributed. So we are building a confidence interval for the mean. So the mean temperature. Remember that when you have a mean temperature, you have two options. If sigma is given, you're going to follow Z. If sigma is not given, you're going to use T. So read the question carefully. You selected 16 coffee shops. You measure the temperature of coffee sold in each of coffee shops in this sample. The sample mean is 162 and sample standard deviation is 10. So it's not sigma. S is given to us, S, or sample standard deviation is given to us. So you're not going to follow Z. You're going to follow T distribution. Very well, so let us follow the guidelines. First of all, verify that sigma is not known. Of course, it's not given to us. This 10 degrees Fahrenheit is sample standard deviation. You can see it in the second and third line of the question. The sample is random? Yes. We randomly selected 16 coffee shops. And the population is normally distributed. This is on the last line. Assume that the temperatures are approximately normally distributed. So the first step is done. We go to the second step. Second step says find the sample statistics N and X bar and S. N is the sample size. We know the sample size is equal to 16. X bar, or the average temperature, is 162. It's given in the question to us. S, or sample standard deviation, is 10 degrees. It's also given to us. Well, what is the level of confidence C? The level of confidence in the question, line 3, says 95% confidence interval. What's the degrees of freedom? The degrees of freedom has a formula. It is n minus 1. N, or the sample size, is 16. So 16 minus 1 gives us 15. This is our degrees of freedom. Very good. Now let us construct the margin of error, T sub C, S divided by square root of N. To find T sub C, you can use your calculator, or in old-fashioned method, you can use table. So let us take a look at our calculator and find T sub C. So I'm going to just share the screen with you and show you how to find your T sub C. So first of all, you need to go to second bars, and then you need to find inverse T. What's the area? Area is 95%, so 0.95. What's the degrees of freedom? It is 15. So let us take a look at our T sub C. It is 1.753. Take a look. Your T sub C is a little bit different here. What's the reason behind it? When you're calculating these values, it's super important to note that you have the area, all right, the area to the left. So when you're going to second bars and going to inverse T, the area to the left-hand side is not 95%. The area is 1 minus 95%, 5% divided by 2, which is 0.025. So let us do the computation. As you can see, it is 2.131. So be careful when you're calculating the confidence level and the critical value associated to it. If you use just 95%, here, it doesn't give you the correct critical value. As we've done before, the value, the area is going to be on the left-hand side. So here you have 95% level of confidence. 1 minus 95% is 5%. Divided by 2, get 0.025. The degrees of freedom is 16 minus 1, or 15, and it gives us negative 2.1314. And then if you round it, you get 2.131. And since it's a critical value, it must be a positive value. That's why you see a positive number here. So this is the margin of error, TC, 2.131 times S for the sample standard deviation 10 divided by square root of n, which is 16. This number is approximately 5.3. So this is our distance. Now the confidence interval has left endpoint, which is x bar minus e, and right endpoint, which is x bar plus e. X bar minus e is approximately 162 minus 5.3 degrees, which is 156.7 degrees. And on the right-hand side, you have 162 plus 5.3 degrees, which is 167.3 degrees. You can say that, hey, with 95% confidence, we can say that the population mean temperature of coffee sold is in between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. You can also use your calculator. To use your calculator, you can go to Stat, then go to Tests, and find T interval. In T interval, you're going to use statistics because you have the statistics of the data. First of all, you need to enter the temperature, average temperature, which is 162 degrees. Then you're going to enter the standard deviation of the sample, which is 10 degrees. Then you're going to enter N, or the sample size, which is 16. In the next step, you're going to enter C, or the level of confidence, 0.95. And let us do the calculation. It says, hey, the interval has the lower bound 156.65 degrees to 167.33 degrees, which is exactly as you see in doing the calculation using the algebra. Again, the interpretation is with 95% confidence, we can say that the population average temperature of coffee sold is in between 156.7 degrees and 167.3 degrees.